So good morning, everyone. I hope I'm clear. My sound is okay with all. Huh?
Yes,
So
yes.
okay, great. So I plan to have this session more interactive, right? So while I'm delivering the session, if you have questions, please ask me. Okay. If nobody asks any question, then I will start asking questions. So if you want to avoid my questions, it's better you ask me questions, right? Otherwise, I'll stop and start asking whatever I'm teaching. Okay. So this way, we are going to have the session more interactive. And again, this is two-part lecture, right? So in the first session, we are going to discuss about reinforcement learning and basic reinforcement learning methods, right? So, what is reinforcement learning? What are the basic elements of reinforcement learning, and how do we formulate a learning problem in this particular method or in this particular domain? Okay. And in the second part of the lecture, then we will discuss deep reinforcement learning method, which are pretty recent, last 4 or 5 years, all the advancement that has come into deep learning, how that has influenced reinforcement learning method, and what are the big results that has come out. Okay, so we'll discuss those algorithm in the second part of the lecture, right? So with this, we'll start. Okay, and let me start with a very rhetorical question here, that what is learning? So let us first try to put this thing in our perspective, that what kind of learning we aim to learn, actually, right? We aim to understand, right? So particularly we are interested in learning with respect to machine, or a learning algorithm, or maybe a computer that can learn, right? So what is the meaning of learning here? So if you ask me, so these are the 2 points how I imagine what is learning, right? First thing is making machines more adaptive towards a task by providing more data as experience. So whenever we say that machine learning needs a lot of data, we provide all this data to work as experience for our algorithm, right? So that they can learn from experience. Now experiences could be good, as experiences could be bad, right? Something learned from a bad experience will come out to be a bad learning completely, right? So you have to be very cautious, right? What kind of experience you're giving to the machine. It's not always dumping a lot of data can give you a good output. Okay. And the second important aspect of learning is we want to provide an ability to learn and improve from experiences without explicit programming. Okay. So traditional programming, what do in traditional programming? We basically write a set of rules in terms of your control methods, right? Like if and if then else kind of conditions, putting functions and everything. What we want is the machine to figure out all these kind of rules that exist in a particular domain without any explicit programming, and we want the machine to figure this out using experiences. Okay, and obviously we use data as experience in most cases with machine learning. But today the kind of learning we are going to study, right, this reinforcement learning, this is an interesting learning where we don't assume that the data is already available. Here the learning happens when your computer, your algorithm actually interacts with the environment in real time, and whatever is the data generated via those interactions are used for learning. Okay, so that's a different aspect of learning that we will deal today. Okay, and obviously I will try to motivate you before going there, that what are the kind of applications and where this kind of learning can be used before we actually delve into what is reinforcement learning, right? Now learning, I hope we set the tone right, that what kind of learning we want to study, and with respect to machines, and then how many learning methods are there, or how to achieve this, right? So if you talk of learning methods, there are a lot more learning methods that are available. Each learning method has their own pros and cons. Okay, each learning, like some learning method are better suited for some specific kind of domain, others are better suited for maybe specific kind of constraints, right? And I have listed of only a few of them here, but even there are many more learning algorithms that are out there. And particularly among these learning methods, today we are going to deal with reinforcement learning and deep reinforcement learning. Okay, so deep learning, we will just introduce deep learning, but we will mostly focus on use of deep learning in reinforcement learning methods, right? Now you must be wondering that if these are all learning method, where is machine learning? Because we don't see, okay, there is something called online machine learning, but we don't see machine learning here in this set of methods, right? So Well, it's there, right? Even what we have listed is the specific methods within machine learning here. Okay, so machine learning is all bunch of methods, let's say, combined together with these three specific legs within machine learning. Okay, so usually we understand machine learning. If you go to any course on machine learning, the first thing that you get to understand is there are two kinds of learning: supervised learning and unsupervised learning. And I hope, since this FDP is going on, you must now understand what is supervised learning and what is unsupervised learning. I don't have to explain it much, right? So in supervised learning, we work with label data, right? The labels are available. Those are the supervisors, right? And then the kind of task we perform is a classification task, a regression task. So for these kind of tasks, if you want to pick a method, then supervised learning is like are the bunch of methods, right? And if you only have your data without label, so we work with unsupervised learning method, right? We usually perform clustering in unsupervised learning method, but even the another task that could be performed is dimensionality reduction. Now there is a third leg of machine learning, which is called reinforcement learning. Now, can anyone tell me, so I'm starting with my questions here itself, right? We are already dealt with labeled data in supervised learning. We dealt with unlabeled data in unsupervised learning. That for what kind of task we should deal with different set of methods within this reinforcement learning framework. So the kind of task I'm talking about, right, or I'm asking you to imagine is where you have controls. Okay, so imagine a task where you want to train a robot, okay, to clean dishes in your kitchen. So the learning task is, right, to learn to clean dishes in my kitchen, right? Take the dishes, clean it, keep it. Obviously, all of us would like to have such a robot in our houses, right? Yeah, it's still a long way to achieve that. But is it a supervised learning task, cleaning dishes? Because we don't have to generate labels here, right? Like given a dish, we don't want to say that whether that dish is dirty or clean. Maybe that could be a sub part, okay? But we know that all are dirty dishes and we want to clean it. Okay? So it is not supervised learning. Okay, it's not also unsupervised learning. We don't want to segregate the dishes that maybe these are, I don't know, oily dishes, and these are not oily or something like that. We don't want to do that also. We want the robot to pick each dish, clean it nicely, and then put it. Okay, so this kind of task, which is neither supervised learning nor unsupervised learning, falls under reinforcement learning task. And if you see the kind of task we just discussed, it is also called control task. Here, what we want to learn is a control mechanism, right? And why control? Because obviously that robot or whatever humanoid robot we can imagine, or any kind of robot, has to apply a lot of controls or learn to apply a lot of controls at how we should pick the dish, what should be the motion of cleaning the dish and all that, right? So that kind of control task is where reinforcement learning comes into the picture. So you see the kind of task performed in reinforcement learning, real-time decisions. Okay, real-time decision making means what actions the robot should apply on maybe different kind of plates while cleaning it, because maybe same action may not be cannot be applied in all. Right? It depends whether it is a cutlery or it is just a plate or dish or a spoon or whatever. Different actions will be required to clean all of them. The task is cleaning. Robot navigation is a very robust, very versatile example. So thinking of robot, you can always imagine these kind of tasks. Okay, but it's not only into robots. Even in games, we'll discuss a little bit about AI games and all that. How computers are getting programmed to beat humans in a lot of chess and very complicated board games and other kind of games. Learning task and skill acquisition. So skill acquisition is a very important thing here. We want the computers maybe to acquire some skills, okay, like driving. Humans, 2 months of training, yeah, we become pretty good drivers. We can drive our vehicles nicely, at least cars we can say. Okay, we are still training the cars to drive by itself though. Okay, so can we acquire the skills of a human? Let's say there is an expert driver who is available. Okay, can we acquire that skill and embed it into a car so that car can drive by itself? We would like to do that, right? Now, acquiring a skill and putting it inside the car, is it a supervised learning task? Where are the labels if it is supervised learning task? Right? Is it an unsupervised learning task? No, again, we are not grouping whatever skills he has in some manner, right? So that again, the kind of learning that required to do that comes under reinforcement learning. So these are the methods, reinforcement learning methods under machine learning that deals with control tasks, wherever any kind of control is required, or you have to execute a kind of control into the system. Okay. So we are going to focus today on this set of machine learning tasks, right? And here are a few examples. Okay. As you can see, all these are different control tasks. Okay. So training a humanoid robot to walk, or maybe training a quadruped robot to walk, or, jumping stairs. Even for a robotic hand, to pick the pieces and put it together, you need reinforcement learning, or even multiple robots playing a game of soccer. Okay. So these are different examples of reinforcement learning tasks. Okay. And these are not only limited to this is just an illustration. Okay. Even you can imagine many more tasks like that. I think I have a slide for that. Yes. Okay. So see, the initial 3 tasks that I have listed are again what we have discussed already: robotic control, autonomous driving, and flying. So making a helicopter fly by itself, right? But all these tasks requires a lot of hardware. So you might start thinking that reinforcement learning is only for hardware, robot, and these kind of tasks where a lot of hardware is there. That's not true. Okay, I said wherever control is required. Control could be software control. Control could also be hardware control. Right? Mostly it is in the hardware, but that doesn't mean such problems doesn't exist. In soft world, right? Software only in the computation world. And I have those examples as well. So if you see this 4th bullet point, it says manage an investment portfolio. So if some of you you do this investment in share market, right, in the stock market, buying a share, selling a share, that is also a control task, or I can say a real-time decision-making task. At every moment of time, looking at the status of the shares and the stock market, sorry, you have to make a decision whether to buy a share, sell a share, or hold a share. Right? And this decision making has to happen for every share for every moment of time, maybe, right? When the market is open, obviously. So this is also a control task and no hardware is involved. Okay, but real-time decision making, control, those things are involved. Similarly, online advertisement. Okay, now for online advertisement, it is both the advertisers and even the platforms which host these kind of advertisement, like Google. Okay, Google would like to make this decision at every moment of time that what kind of ad it should actually flash for what kind of users at what time and kind of things, so that obviously revenues can go up. Right? So that also becomes a control task. It's not supervised learning and unsupervised learning only. It becomes a control task because there are other controls that are involved in advertising. Control of smart grids. Right? So nowadays, this is a very hot topic, I guess. A lot of research is going on in creating smart grid, where you want to balance the demand and supply of a smart grid. You want to predict what would be the demand of the day or demand per hour, right? So that again can be converted to a control task, and you can apply reinforcement learning methods there. Okay, humanoid robot walking we already saw. Playing many different Atari games better than humans. So why I put it, because this deep reinforcement learning era around 2013, 2014, right? Just after when we got this big news of deep learning, with image processing giving very good results, then the era started with this particular work or particular paper. We'll actually discuss that in our second session. Okay. Then in the last decade, in 2016, there was a big news that Google's some AI computer has beaten world Go champion in some game. This was like the biggest news after IBM has defeated Gary Kasparov in chess in 1999. Right. So that was done again using reinforcement learning. So this defeating the world Go champion. Go is a game, a board game, which has a lot of state space. The state space is in the order of 10 raised to power 140. And because of that, it is very complex for the computers, right, to beat humans in that game. But well, Google's DeepMind came with a solution, and that solution used a lot of reinforcement learning elements. It was actually developed using deep reinforcement learning methods. Okay, and just last year in 2020, the same Google's company has come up with protein folding. Okay, so they could predict now protein folding, which is now a big news even in the biotech field, where which has been a challenge in biotech field, that how to know the protein structures and how do protein folding happens. But it seems now a computer program can create that or predict that with maybe more than 90% accuracy. Okay, so you can see the kind of applications that this reinforcement learning have is actually a lot, enormous. Okay, and wherever you have any kind of control task, you can actually model that problem as a reinforcement learning problem and implement a kind of learning there. Okay, so I hope I'm able to motivate you that why we want to learn reinforcement learning, what is the use of it, okay, and how it is different from other machine learning techniques, which are supervised learning and unsupervised learning techniques, which are obviously famous and they have their own merits, right? So with this, now we will delve into reinforcement learning. Let us start discussing that, how do you formulate a problem in reinforcement learning? I hope all of you understand. In any learning task, the first very important step is to first formulate the learning problem, because unless you're able to formulate the problem properly, you won't be able to solve it, right? So we'll do the same. First, we'll try to give the problem a structure. We'll try to formulate the reinforcement learning problem. We will see that, what kind of things we can learn or what kind of parameters, we can solve for. And then we will discuss the solution methods. And we will go through a few solution methods. Okay. So this slide actually provides the overall architecture of any reinforcement learning process. Okay. So in reinforcement learning, we always have something called an agent. What is an agent? An agent could be your computer program, could be your robot, could be an algorithm. So whatever you're trying to train is the agent. Okay. Or we always say in reinforcement learning that it is the agent that is trying to learn. Okay. So the learning is focused on this particular agent. Now in reinforcement learning, the agent, well, the task is, I hope you get by now, the task is kind of real-time decision making. At every moment of time, this agent has to make decision based on some input, output, environment, and everything. Okay, but the task is to take a decision. Whenever we take a decision, what is the outcome of that decision? So usually, whenever you take a decision, the outcome is you fix an action, a course of action, right? That is the meaning of decision making. That there are multiple course of actions available, and you decided that we'll go with this course of action. And the same thing happens here in reinforcement learning. Okay. So the agent, it always has a set of actions available, and the aim or the objective of the agent is to choose one of the action. Obviously, it would like to choose the best action, but nobody knows what is the best action, right? So the task becomes to learn the best action. And we will see how the agent learns the best action. But for now, let us just imagine that at every moment of time, agent chooses or takes an action. So he chooses an action, and then that action gets applied onto the environment. So this is some kind of an environment, automatic, what you call smart warehouse, where a lot of robots are only there. Amazon and these big companies are already doing this. They have warehouses where only robots are deployed. So yeah, so the agent takes actions on the environment, and whenever any action gets applied on the environment, like whatever, if the agent just decided to move forward 4 steps, let's say that is an action, right? Any kind of action will change the state of the environment. So whatever was the state of the environment previous to application of the action has now changed, because even the agent has moved, the position of agent has changed, so the state has changed. Or maybe the agent is moving some box from point A to point B, then also the state of the environment will change, right? So whenever the agent chooses an action and that action gets applied onto the environment, the state of the environment changes. Right? This change in the state or the new state of the environment is again perceived. So that is why this arrow is returning back to the agent. That this change in the state or the new state of the environment is again perceived by the agent, and with this perception, he again makes a decision on now what is the next action to get applied, and this circle goes on, right? And just by following this particular applying action, observing, applying action, observing, the agent starts learning. Learning what? Learning to improve upon the actions that it is executing on the environment. Okay. And one important element that helps the agent to learn about improving the action is something called a reward. Now, what is a reward? So the reward is whenever an agent applies an action to the environment generates some kind of a reward. Obviously, when you are the designer of the system, you have to encode those rewards into the agent. But for reinforcement learning perspective, these rewards are always coming out of the environment. So the rewards are embedded into the environment, and the rewards are received as an outcome of the action. So we are not going to actually today discuss that how to design the rewards, because in reinforcement learning, it's always the assumption that the rewards are received from the environment, and it is always the output of your action. Okay, so I give you an example. Let's say the agent task, there is a robot which is an agent, and the task of that agent is to move from some point A to some point B into the environment, right? So for moving from point A to point B into the environment, it knows the destination. It decides the action is to maybe to move forward 2 steps. If it moves forward 2 steps, right, and that action gets applied, obviously the state of the environment has changed, right? Now, the reward could be in terms of what is the current distance to the destination. So if the current distance has reduced, then maybe the agent can take that as a reward. However, the agent can also decide on an action that move backwards 2 steps, because initially the agent doesn't know which actions are better, right? And if it decides to move backwards 2 steps, and then it checks what is the distance to the destination, the distance has increased, that can again be given as a reward, but it will be a negative reward. So the rewards could be positive, rewards could also be negative, right? And it is these rewards and the state that helps the agent to improve. Okay. Now, how this whole improvement happens is what we are going to study today. Okay. I hope no questions, right? Nobody has any doubt, any question? Okay, good. So this is how, so in the last slide, we described the problem at a very higher level, like a story. Okay, but we have to solve it. We have to get into the mathematics of it. Only then we will be able to learn some function or something, right? And a mathematical framework that helps reinforcement learning to formulate the problem and then to solve the problem is called Markov decision process, MDP. I hope many of you must have heard about Markov process, a Markovian property, right? Even naive Bayes in supervised learning uses Markovian property, right? The naive Bayes algorithm, if you remember. Okay, so yes, it is like an extension of those kind of. So it is basically a Markov process. What is a Markov process? So basically, you have states and you have transitions between the states, right? So from one state you transition to next state, and then from that state you transition to another state. We call it a Markov process, right? With a transition function. So there's a probability of transitions, right? However, in Markov decision process, some more elements are there. Okay, and reinforcement learning, can be described using this mathematical framework. Okay, so how do we describe an MDP? So an MDP is described by a set of states. So we are going to assume that the environment has some finite set of states. Okay, if it has infinite set of states, the problem becomes too difficult. And even in real world, you cannot have the whole set of states, right? So we'll discuss those issues later, but let us keep the problem simpler for now so that we can build the understanding on it. Okay. So the MDP has a set of states, which is with respect to the environment. Then there are a set of actions, okay, so which is with the agent, right? So in each state, the agent has to choose one of the actions from this set of actions. Then there exists a transition function. Big assumption here, a transition function which tells us that if the agent is in state S and the agent decided on some action A to execute, what is the probability of going to some next state S dash? Okay, so the environment behaves based on this transition function. Okay, or what would be the next state of the environment after the agent executes some action A is determined by this transition function. It is also called model of the environment or the dynamics of the environment. Okay, and we're assuming that these probability values or this transition function is given. Okay. Later we will relax this assumption, but for now, let us keep this assumption. Okay. In a typical MDP, like this is always there, but in true reinforcement learning problem, we don't have access to this transition function. Okay. And then there is a reward function. Again, we are assuming, as I told you, the reward function is given. It is part of the model. So all these state, action, transition function, reward, these are already given to you. And then you have to formulate the reinforcement learning problem and solve it. So what is the problem? We'll discuss. Okay. Then there may exist a start state or a distribution over the start state. So, what is the beginning of the whole learning process, right? What is the beginning state that is given? And there may exist a terminal state, may not exist a terminal state. Okay. So if you have episodic task like the game of chess, okay, you're training the agent to play the game of chess. Everybody knows that either, after some 40, 50 moves, it will be a draw, a win, or a defeat, right? So terminal state exists in that particular game. But if you have like a continuous control game, right? Let's say maybe self-driving car. Okay. So for the self-driving car, maybe it can drive very long. Okay. So there is no terminal state as such. Okay. Means the decision making has to go on until the car can drive. Okay. There's no fixed decision making that you can say on 40, 50 steps, this will end and a new episode will start. This episode just continues till maybe until the battery dies or whatever. Okay. So that's why it is written that you can have continuous, task MDPs, or you can have these episodic task MDPs. And in episodic task, you can have terminal states, which makes our life easier. So most of our discussions, we are actually going to assume that the tasks are episodic task and there is always terminal states. Okay. But then there could be tasks without terminal states. And then, yeah, there are ways to, like we're going to actually, the formulations that we will discuss will apply on both kind of cases. Okay. Now, the question you might be thinking is, okay, all this is okay, but what are we learning? That has not been discussed. Like, okay, something was discussed that the agent wants to learn the actions, right? But how that problem is formulated. So this is the first slide that actually starts talking about the problem or the objective. Okay, and this is called policy. So policy is a very important element of reinforcement learning or even solving an MDP. Okay, and what is a policy? It basically describes agent behavior at any given point of time. Okay, so what is agent behavior? What do we mean by agent behavior, or for that sake, anybody's behavior? Right? So anybody's behavior is defined by the actions they perform, right? That is what we say, right? Like you will define anybody's behavior by looking into what kind of actions they perform, right? In the world, in the outside surroundings. Okay. Same applies for the agent. So policy is nothing, but it is a function, a mapping, right, that tells the agent what action to take in each state. So if you remember, right, earlier we said the agent's aim is to find the best action in each state. And now we're giving that a name that, let us construct a function, and we're going to call that function policy. And that policy now will tell the agent what action to take in each state. Okay. Now, once you have defined such a function, you can have a lot of variety over that function, right? So you can have a random policy. What would a random policy do? Right. So a random policy would be where obviously the agent will choose actions in any state randomly. Right. So a random policy will create a random function, and that random function will map state to action just uniformly at random. Right. So with this, obviously you can have a random policy, then maybe you can have a policy which is better than random policy, right? Where maybe the actions are chosen in a state in more informed manner, right? In a similar fashion, if you keep on going forward with a variety of policies that you can have in a particular MDP, right? At the very best you can do, right, is to choose the best action that you can apply in each state, and then you can call that as an optimal policy, right? Once you have got the optimal policy for a particular MDP, can you improve upon it? Well, if you can improve upon it, it's not an optimal policy. And if you can't improve upon it, then yeah, you have actually hit the optimum, right? The maximum that is possible. And that becomes now the aim of reinforcement learning, right? The aim of reinforcement learning would be to find an optimal policy for the MDP we are going to describe. Right? The MDP contains all the states, action, transition function, reward function, everything. And then the aim is to find an optimal policy using the MDP. And what is optimal policy? Choosing optimal action in the states. Okay. Now, how do you encode this policy function? Well, this could be a very simple lookup table, because this is nothing but a mapping of state and action. So if you can enumerate all possible states in the system, let's say you have only 100 states in the system. For each state, you can maybe write the optimal action, and that will be a policy. Or it could be a very complicated function, right, which takes the current state or feature of the state as an input. It could be a function which takes the features of the state as an input, and then tries to come up with maybe a probability distribution over the actions. Okay. And those kind of policies are called stochastic policies, where for a particular state, not a single action is fixed, but a distribution over the actions is given. Okay, so the policy can have a lot of variety, and the whole reinforcement learning is about learning a policy function, learning the optimal policy function. And we are describing or bringing the notion of optimality here. I'll describe that notion in more detail in later slides. Okay, so the policy is the core of reinforcement learning. Okay, and in that sense, it is alone sufficient to determine the behavior of the agent. So we describe now one technical element here, which is the policy. Okay. The second most important element in reinforcement learning is reward function. And this reward function actually defines a goal. Okay, so we earlier said the goal is finding the optimal policy, and now we are saying reward defines the goal. So there must be some connection between reward and optimal policy, right? Because it is saying reward defines the goal. So somehow reward should define the optimal policy. So we have to come up with that connection. We will come up. Okay, but let us see that how these rewards behave. So the agent's sole objective actually is to maximize the total reward it receives over the long run. Okay, what it is saying in reinforcement learning, the agent's objective is to maximize the total reward. However, earlier we discussed that in reinforcement learning we should learn the optimal policy. How the two are connected? Well, what did we discuss? Whenever the agent takes an action onto the environment, it receives reward. If it will take the best action in the environment, the reward will also be the best reward. Right? If the agent always takes the best action in the environment, then the total reward it will receive, right, by taking all the best actions will be the maximum possible reward. And we discussed that if you have reached optimal policy, you cannot improve upon optimal policy, right? Because that's the best you can do, right? So if you just focus on maximizing the reward, the maximum reward you can achieve into the environment, right? Then the policy that must be used to achieve that maximum reward must be an optimal policy. So just take a second to grasp that, right? Whatever I said. I said if the agent only focuses on maximizing the reward, it wants to achieve the maximum reward possible in each state, okay, then the policy used to achieve the maximum reward, total maximum reward, must be the optimal policy. Makes sense, right? I hope you can get the connection. Okay. So we're going to exploit this connection a lot actually going forward. Okay, right. So as we said already, the environment provides the reward given the state action in the next state. Okay, and the reward actually acts as the basis to alter a policy. Now, what is the meaning of altering a policy? This is interesting. Okay, and we will see. Okay, so keep those things in mind. We will describe those even in more detail in coming slides. Now, in general, your rewards could be stochastic function. So, in a very generic manner, we cannot say that for every action the same reward will be received, because it depends on a lot of things. I give you a taxi example. Okay, so for a taxi, right, picking passengers from some location could be a reward. Okay? But every time that taxi will visit that location, the taxi may not get the same amount of passengers, because passenger may be time dependent. So in the morning hours where everybody is going to office, there will be some location where a lot of passengers would be available. In the same location in the afternoon, no passenger will be available. Right? So the rewards are changing, although the state is same or maybe action is same. Right? So this is one particular example. So reward could be stochastic, right? Could be again follow some kind of distribution, or could be static. For simplicity, let us assume static reward for now. Let's make our life easier to understand the algorithms. Okay. Right. Now, how these rewards and policies affect each other. This is very important to understand. And in this slide, I have the same thing. Okay. So I'm going to describe you an environment, which is this grid environment, which is simply 4x3 grid environment. Okay. In this grid environment, there is one cell, which is block cell. You cannot enter, or the agent cannot enter this cell. Okay. And there are two exit states. The +1 state where the agent exits the system with +1 reward, and a -1 state where the agent exits this whole grid with a -1 reward. Okay. And then there is something called a living reward, or the reward inside other grid cell. Okay. And which is here written as -0.01. So whenever any action gets executed in other cells, the agent gets the reward of -0.01. What are the action? I think very simple. You can imagine there are only 4 actions possible. Diagonal movements are not allowed. So the agent can go up, down, left, right. Okay. And then there is some stochasticity into the environment. There's some noise in the environment. Okay. In this particular grid environment. What is the noise? The noise is whenever the agent takes an action. So let's say the agent takes the action to go left. Okay. There's only an 80% chance that it will actually go to the left cell. Okay, and there is 10% chance that it will either go towards the upside cell or may try to go towards the downside cell. Okay, so there's a 10% chance of going on the left or right of the intended action. Okay, so this is how the environment is configured, and this arrow shows the optimal policy learned using some reinforcement learning algorithm for this particular environment with these settings. This is the optimal policy learned. Okay. And I have the same environment again, and see, everything remains the same. I'm just changing here. If you see at the bottom, the rewards. Okay. And just by changing these rewards, the behavior you can see actually changing. Okay. So I have 4 different kinds of rewards for the environment. Problem is same. Right, reaching, maybe exiting the system with maximum reward, and exiting the system with the maximum reward is obviously you want to exit at the +1 state, right? But here you can see these arrows. These are the optimal policies. Optimal means the best that the agent could find or could do in these environments. And the optimal policy just tells you what is the best action in all the states. Okay, and you can see those are changing, right? In all of these, those are changing, and specifically I want you to focus on these particular states which just got highlighted. Okay. See the first one, it is very interesting. In the first one, with the reward of this -0.01, the best action in this particular state, which you can call 4x3 state, 4x1 state, right? On the bottom right state, the best action that the agent found is to actually hit the wall, go downwards. How can this be best action? Think about it. Okay, how come hitting the wall is the best action? And once we change the reward, it aligns, it becomes better. So it is now saying, okay, going left is the best action, because the aim is to reach this +1 state, right? There only the maximum reward is there. Okay, if I further make this living reward more negative, right? This remains the same, but you can see from the other side, it is taking even more shortcut to reach the +1 state. And then the last one with -2 negative reward, see the AEP is, the agent just says that, yeah, go to -1 state and exit the system. Right? So what you can see here is the way rewards are configured into the environment that changes the optimal behavior of the agent. So if you are the system designer and you have to actually fix the rewards into the system, if the rewards are not properly configured, you're not going to get the best behavior of the agent, as or maybe the expected behavior of the agent. So it's not the fault of the agent. It may be the fault the way you design the rewards for the agent. Okay. And again, to answer this, why the agent is hitting here, the bottom, the wall, or not going, because the agent is actually trying to play the safest possible in this particular first grid. Okay. What is safe here? Well, if the agent takes the left action, and just going left, there is a 10% chance that it may end up in this -1 state. Right? So if the left action is done 10 times, out of 10, there is one chance that the agent may end up in this state. The agent here wants to even avoid that. The agent never wants to hit this -1. And how to achieve that? Well, it starts sitting downwards, and while it is sitting downwards, there is a 10% chance that it will definitely reach this state. Okay, so it may take more time, but in this first solution, whatever the agent policies the agent has found, it will never enter this -1 state. It has made sure of that. However, when the rewards become more negative into the environment has become more negative, it starts taking risk. So the agent going left is actually a 10% risk, right? So, and accordingly, you can see that when the environment has become very negative, it doesn't take any risk or anything. It says even getting -1 and exiting the system is better than getting any -2 reward in this environment, right? So I hope you understood the connection between reward and policies. Okay. And then these are the set of methods that we can use to find the optimal policies. So I have listed all possible RL methods here. You can segregate these methods in model-based methods and model-free methods. Okay. What is model-based method? Where we use the model of the environment, right? The transition functions are given. Okay. And under model-based methods, we have dynamic programming-based method, or two famous methods within dynamic programming are called policy iteration and value iteration method. In today's section, we'll actually touch upon these two methods. Okay. And then there are obviously approximate dynamic programming methods, wherein we don't assume that the model of the environment is given, but by interacting with the environment, we try to approximate the model of the environment. And once we have approximated the model of the environment, we go back and use these two methods, policy iteration, value iteration, to solve our problem. Right? Then there are model-free methods, wherein there's no assumption that the model of the environment is given. We still want to solve the RL problem though. Okay? And what is the meaning of solving RL problem? Well, find a policy that maximizes the reward, because that policy is going to act as optimal policy. Okay. So in model-free methods, you have Monte Carlo method. We are not going to discuss Monte Carlo, not that much time, but yeah, if you're interested, read about it. Then there are temporal difference method. In short, they're called TD methods, and these are the most famous reinforcement learning method among all methods. Most famous ones are TD methods. Okay. Within TD methods, there are two particular methods called SARSA and Q learning, and even among the TD method, Q learning is a very well-known method. Okay, and today we are going to discuss Q learning as well. Right. Then there are other advanced methods, right, that sometimes combine these methods, but yeah, these are also you can say model-free methods. Okay, so and these are more advanced methods. Right? So all these deep learning and everything that has come in actually improve these methods a lot. So there are value-based methods. What is a value? We will discuss. A value is made up of these rewards that we have. Okay, so we'll discuss that. And these methods focuses on the value. So all these policy iteration methods, value iteration methods are actually value-based method, where they focus on some value of the state, right? And they just keep on improving the value of the state. Okay, and once they converge with the true value of the state, then they take out the optimal policy. Sorry. Then there are policy-based methods, wherein these methods directly work on policies. Okay, so they do not look into these value function or value methods, whatever are there. They directly look into a policy and then try to create another policy which is better than the previous policy, and just try to keep on improving on these policies only, on the policy space only. Policy-based methods are more suited for continuous control tasks. So if your actions are continuous, usually people go with policy-based methods. Those are more suited for those kind of tasks. However, if your actions are discrete action, playing a game of chess, right? These are very discrete action. People go with value-based methods. Okay? Then there are methods that combine the benefit of both these methods, and those are called actor-critic methods. They use policy, they directly work on policy, but they also use the values. Okay, so this is the whole very high level set of methods that are available to solve reinforcement learning problem. And if you're interested, you can go and look and read about these methods in more detail. Okay. So now whatever time we have, right, this half an hour will become a little more technical, where we will actually start formulating our cost function, formulating our these goals or objective functions, and then we'll see that how we will solve it. Okay. So as we said, the goal in reinforcement learning is to maximize the reward. Okay, so we can call it, or in reinforcement learning we also call it returns, right? And how do you define a return? Basically, for any time t, the return is going forward from that time till the end of the episode, right? So we're assuming episodic task, going forward from the time till the end of the episode. What the agent does, agent takes action in each state, right, until it reaches the terminal state. And whatever action that hasn't taken, there's always a reward. So if you sum all the rewards going from a time till the end or till the terminal state, right, that sum is called a return. Right? That is the goal. So how it is the goal? So what the agent wants to do is, it wants to maximize this return. So at every point of time, okay, the agent wants to choose the actions into the future time step such that the sum of those rewards that it will receive gets maximized. Okay. There's one important thing here. So this is a simple expectation for one particular episode, right? It is nothing but just sum of the rewards that the agent can receive. However, if you see the definition, it says expected return. Why expected return? Okay, so it is not this simple return, but it is expected return because in the same state, in the next episode, when the agent is visiting the same state, it may choose a different action, right? So we are talking of returns, right? So returns is nothing but sum of rewards on the current time step till the terminal state. And an expectation is involved because the agent can choose different actions in the same state. Okay, so there might be a probability distribution over the actions. So every time the agent is visiting a state, with some probability it will choose one action, with some other probability it may choose another action. Right? Initially, when the learning is happening, right, there may be a probability distribution over this thing, and that's why there is an expectation, or it is called expected return. Okay. Now there is one problem with this definition of the return. The problem will occur in continuing sequence or continuing task. In continuing task, when would the episode will end? It will end at infinity, right? Because the task just continues. If it ends at infinity, right, it doesn't at some time point, then the returns will also be infinity. Any number sum to infinity will be infinity. And that is a trouble for us, because then this g of t, the return definition, becomes indeterminate. We cannot define it, and we can't define this. How do we solve the problem? Okay, so to get rid of it and to have a more general definition, a generic definition of return, we use some technique called discounting. Okay, what do we do in discounting? Basically, it's very simple and very elegant as well, if you ask me. We take a parameter gamma, which we call the discount rate factor. Okay, this parameter has value between 0 and 1. Okay, so it has only value between 0 and 1. And then we multiply this parameter with all the future rewards that we are receiving. Okay, and as we go forward in time, we keep on increasing the index of this return, this factor gamma. What this do? What is the effect of this? Well, since gamma is a value between 0 and 1, if you keep on increasing the power of gamma, the value will become smaller, smaller, and smaller. Right? That means if I take the sum, if I multiply the future rewards like this and take the sum of it, then the rewards that appear very late, after let's say 10th or 15th time step. So 15th time step, and let's say gamma is 0.5. So the value will be 0.5 raised to power 15 multiplied by the reward. that reward will almost be equal to 0. Okay? So this way, this putting this factor gamma actually bounds my reward. Like it gives, like, the effect is the reward that appear very late, the effect of those rewards are minimized on my current return value, this g of t value for a particular state. Okay, and that helps me to bound my g of t. So now I can always calculate my g of t, because it is not going towards infinity, it is actually going towards 0. So you will start with very high reward rt plus 1, and as you go forward in time, the value of the reward is decreasing, right? So the summation finally will be a finite summation, or it will be a bounded summation. Okay, and now the aim simply becomes, because this summation actually sums all possible reward, right? And we can define this sum for each state. So now the aim simply becomes to maximize this sum. If we can maximize this sum by whatever actions we are choosing, right? If we maximize this sum to a limit that it is not possible to even maximize further, we have solved the RL problem. Okay. So with that definition, right, we define something called value functions. Okay. And value functions are nothing, but it is just generalizing this definition of return or sum of rewards or sum of discounted rewards using the discounting factor. Okay. So these value functions are defined over the states. So we can define value function over the state called state value function, or it is also defined over state action pair, usually also called Q value function, or also called state action value function, or only action value functions. Okay. What does these value function tell us? So please try to hear this very carefully. The value function of a state, okay, is the total expected reward. Okay, total expected reward that you can receive starting in that state and going forward into the future. So for any state, the value of that state tells us that if I start from that state and I follow some policy pi, some pi is given to me, right? Somebody gave me the policy to be followed. It's may not be an optimal policy, but under that policy, what is the value of a state? Which is basically saying, if I follow that policy and I start in some state S, then how much reward I can collect? What is the maximum reward I can collect? Okay, and this is actually, it is very simple. It is just writing the same thing, summation of all the reward multiplying by this gamma factor, right? And taking an expectation over it. Why expectation? Because your policy, can give a distribution over all the possible actions that you have in the state. Right? Same definition now you can have for state action pair. So it is, again, in more detail you can see. So in action value, it's not only the state, but it also fixes the action in a state. So this value function says that in a particular state, if I decide or if I choose action A, then from that point going forward into the future, how much reward I can collect. And this is called state action value function. Okay. Now, since we have defined these value functions, we can bring in the notion of optimality back into the picture. How do you define an optimal policy? Okay, so this value function actually provides us some kind of metric or some kind of instrument to judge a policy or to evaluate a policy. See, till now we just discussed that policy is behavior, policy is taking action. But now once you define value function, and the value function says that for a particular policy, right, what is the value of each state? Like how much reward you can receive for each state. So if you have two policies, pi and pi dash, if you have two policies, we can say pi is a better policy than pi dash if and only if the value function of the states under pi is greater than the value function of the state under pi dash. Whichever policy gives better value function is a better policy, right? Or reverse is also true. Whichever, let's say we have the maximum value function, okay? So the policy which gave us the maximum value function is actually the optimal policy. Right? So I hope you could understand the connection, and this actually helps us a lot. Now we can simply focus on these value functions, right? And we try to learn the best value function for every state. Okay. Once we are able to learn the best value function, we can actually look into the policy that it gave us the best value function, and that is our optimal policy. Okay. There will always be one such policy. So in any MDP, right, you will always have at least one optimal policy. There may exist more than one optimal policy. Okay, but at least one will always be there. And another interesting fact here is all optimal policies have the same value function. So the value function of a state under any optimal policy in that particular MDP remains same. Okay. So now we just have to solve for these value functions. So there are these Bellman equations which establishes some kind of a recursive relationship between the value functions of the state. Okay, so it basically how it helps you is whatever that expectation E we had earlier, it removes that expectation and plug in the real probability values. Okay, so the value function of a state in model-based formalization is defined with respect to the value function of other states. So it is a recursive relationship you can see, and all other things if you see. So the first summation is over pi of A given S. It is the probability of taking action A in a state S, right? Which is known because somebody gave us the probability. We want to find the value function of a particular policy. So these policies are given. Then we are also assuming the model of the environment is available. So this P of S dash R given S and A is the model of the environment which is given. Okay. Reward at every point of time, whenever you execute an action, you will get the reward. So reward is known in that sense, or at least distribution is known. So we know the reward. Okay, gamma is a parameter that we set. So gamma is, you will set 0.5, 0.9, some parameter. The only unknown in the system is this value function, V pi of S, V pi of S dash. And you have to write this equation for all possible states into the system. So if you write this function for all possible states into the system, what you will get is a set of linear equations. And you can always solve a set of linear equations and find these value functions, the optimal value function, right? The best value functions possible. Okay. If this policy is an optimal policy, then there is another equation called Bellman optimality equation, that is applicable, and that is only applicable for optimal policies, where you don't have to take the summation over all possible probability values of actions. You can just choose the max over A of this summation, internal summation, which remains the same. Okay. Now using these functions, we actually come to the methods to solve the RL problem. So the first method is called policy iteration method. Okay. Now, how does this method work? So this method involves two steps: policy evaluation and policy improvement, right? And we iterate over these two steps. Policy, like first we evaluate a policy, then we improve the policy, again we evaluate, improve, and we keep on iterating over these two steps until we reach the optimal policy. So here at the bottom, you can see we will start with some policy pi naught, which is, let's say, a random policy or some arbitrary policy. Okay, we can evaluate this policy, and what we will get, the value function under this policy, and what is the value of all the states under this policy, right? Once we received all the value, then we will use some improvement. Okay, so there is a simple equation for that. We'll actually choose a greedy actions, or we'll tell you what the improvement is, and then we will go a better policy pi 1, and it is guaranteed that pi 1 will be a better policy than pi naught after this improvement is done. Since pi 1 is better than pi naught, we can actually come up with pi 2 better than pi 1, and we'll keep on doing this until we have pi star, which is we cannot improve it further. And this method is called policy iteration method. Okay. So whatever I just described you, same thing is written in this slide in terms of like steps. Okay, how to come up with the iterative solution. So what we are doing is, initially we are taking some policy pi naught as input. Okay, and then the first step is getting executed, which is called policy evaluation. In policy evaluation, what do? We solve those equations, but instead of solving equation, we do an iterative solution. Okay, so we assume that there are a sequence of value functions that exist. Okay. Initially, we initialize all the value function V naught with some, let's say, all zeros. Okay, and then we use this particular equation which is the same as Bellman equation, right? To calculate the value function of the next iteration. So we use the value function from the previous iteration to calculate the value function of the next iteration. And then we keep on doing it until these value functions converge. Once the value functions converge, policy evaluation is over. Then we go into policy improvement. And what happens in policy improvement? Well, we create a new policy, we construct a new policy. Okay, so we are constructing a new policy, right? How are we constructing the new policy? Well, we just choose the action. We just choose the action wherein this whole summation is maximum. So using the value functions that we found in using policy evaluation, we plug in this equation. So this is called greedy action selection. Okay, because we're choosing the action that gives the maximum value. So it is also called greedy action selection, right? So we, in this system, basically we extract a greedy policy out of all the value function that we learn. And there is a theorem that exists which says that this policy will be better than your previous policy. So we keep on alternating between these two steps, and ultimately you will find your pi star, the optimal policy. This is the solution. Okay. Another method to achieve the same is called value iteration. So that was policy iteration, more focused on policies. This is called value iteration. It only focuses on value function. In the process, it never actually computes the policies. Okay. So the thing is, in value iteration, it uses the other equation, the Bellman optimality equation, to do value updates. Okay. So you can see it is max over A, right? And the rest remains the same. So again, you will going to have a set of value function, or these value vectors you can call for each iteration. You create your next iteration value vector using the values of the previous iteration. So for k plus 1th iteration value vector, you create using kth iteration value vector. Sorry. And then you update all the value vector and keep on doing it until your value vectors are not, the values in the value vectors are not changing. Once you find the final value vector, which is the converged one, you then use this greedy policy improvement step, extract a greedy policy out of all the value function you learned, and this will be an optimum policy. This is also guaranteed using a theorem. We are not going to discuss that. But these are the two basic methods to learn a policy in model-based formalism. Okay. I have the pseudocode here. Like, it's pretty simple pseudocode, right? So yeah, you can go through. And I have this example. Again, you can see this is the same grid example that I used earlier. Okay. And I have a few set of snapshots that how running a value iteration looks like in this particular setting. Okay. So initially, all these numbers just denote the value of all the states, right? So these are simply the initialized to 0. So initially, all the value of all the states are 0. Okay, and we are going to use this function to calculate the value function at first iteration. Okay, so in the first iteration, to come up with v1 of s, you will use the value at v0 of s, where all the values are actually 0. Okay. So in the first step, what you'll find actually wherever the reward is non-zero. So here all the living reward is 0, not negative. Okay, discount factor is 0.9, and the noise is the same amount of noise in the system. Okay. So in the first step, you'll find that okay, only these two states discover their values, other still remains 0. Okay, and as you go forward with value iteration, you see the positive value or this information about the max reward state starts spreading, but this negative state value just remains there. This is the second iteration of value iteration method. Third iteration, the value starts propagating even more. Okay, and slowly, as you can see, right, this high value is somehow propagates to all the states, right? That means if I start in this state, right, then I can get a maximum of 0.19 reward going forward into the future. Means there is a chance of actually getting -1 reward also. And in some total, if I do 10 or 100 trials, I'll end up with this 0.19 reward. In this case, in this particular policy. Okay, this is not the optimal value that has been learned. This is some intermediate value, right? So you can now keep on doing this. Okay, now these are the values at the 10th iteration. Now you see 0.85 for this state, 0.74 for this state. You can keep on doing it, and you see after even 100th state, the value here is still 0.85 and it's still 0.74, but the values of other state has improved. Okay. Now from this 12th to 100, you see the changes are very minimal. Only few state values change, other become static. And after 100, even if you keep on running value iteration, none of the states value have changed, will change. Okay, so that simply shows that the values are converged. Now you keep on running value iteration any number of time, the value of these states will not change. Right? So then when this happens, that the value states are not changing, then the actions with respect to these values, right? These are the actions that are learned. Right? These makes your optimal policy. Right? And you can do the same for Q values, wherein you learn a value for every action of every state. So here you learn the value of every action in all the states. Right? Here also you can see the best value are still the same, 0.85, 0.74 here, 0.48 here. Right? So the best value is for the best actions only. So you learn any Q value or value of the state, the final answer to the puzzle is same. Right? So the final optimal policy will be same. Okay. So these were model-based methods. Now we are going to go through one basic model-free method, which is called Q learning. Okay, and then we end this session, right? So under model-free method, I told you, right, this temporal difference method are the famous method, but the approach remains the same. So in model-based method, we focused on learning these values of the state, and then once we found the best value of that a state can have, we then stopped and then we extracted the policy that got us the best values, and that was the optimal policy. That is what we are saying, right? Same thing happens with temporal difference method or this model-free method. However, one important element is missing, which is the model of the environment is not available anymore. And since model of the environment is not available anymore, right? How do we solve this problem? Well, we have to now interact with the environment even more. Okay, so we have to collect samples from the environment. We have to choose an action, apply that action, see what is the next state, see what the reward we got. We collect everything. Hey, and from that collection, we improve our value estimates of the state. And then we again go back to the environment, execute an action, and collect the sample. And this is what happens in temporal difference method. Okay, so in temporal difference method, the value of a state is updated based on the current value, whatever value you have, okay, plus some alpha times. This is a new parameter. You can call it step size or learning rate. Okay, so based this alpha parameter we use, okay, and then we calculate something called TD error. Okay, the TD error is given by your current reward plus the same gamma factor, the value of the next state that you went to, okay, minus the value of the current state. This is called TD error. So you improve your value of or value estimate of your state, right, with the current error that you can record with the current sample. Okay, and this way of updating the value function is called TD0 method or one-step TD method. Right, and this is this TD error, which is the error with respect to your time, right? Because you are in current time t, and then you're taking an action and going to the next step at time t plus 1. So what is this time difference error, which is used to learn the value function, and that's why the name is temporal difference. Okay. Now, one famous method in this TD learning or TD methods, again, there are a set of TD methods available. One famous method is called Q learning method. Right? What is Q learning? So it is also called sample based Q value iteration. It is going to execute value iteration as we saw earlier. Right? However, it will collect samples from the environment, and for each sample, then it will estimate the value of the state or value of the Q value of the states. How that is done? If you see, the equation almost remains same. So you've learned the Q value of a state, okay, using its current Q value plus some alpha times the reward that you just got plus gamma times. Now you choose the maximum Q value from the next state. Okay, so whatever is the next state in the system after you execute the action, whatever is the next state you're going to, you choose the maximum Q value of that next state. So there are multiple actions in the next state. You choose the action which has the maximum Q value and take that Q value, and then you sum it up, okay, with and take the difference with the current state's Q value. So this is how you now define your TD error, and you learn on this error. Okay, so the steps are enumerated, which I just told you. Okay, so whenever you interact with the environment, you receive a sample, right? After receiving a sample, you look into your old estimate of Q value, you create a new sample estimate, okay, and then take. So basically, if you solve this, right, you incorporate the new estimate, by taking only alpha weightage of that new estimate, and with 1 minus alpha, you incorporate the old estimate. If you solve this, like, take alpha common and everything, you'll end up with the same equation that is there at the top. Okay. So how this is happening? Okay, let me give you some visualizations. I just have 2 more slides, so I'll not take a lot of your time now. So I'll just give you some visualization of Q learning. How does this takes place, right? So in Q learning, what we are doing is basically we are maintaining something called a Q table of all possible state action values. Right? So what will be the size of this table? It will be S cross A, right? The size of the table will be S cross A. That is the number of entries possible in this table. Let us initialize all these entries or all these state action values with 0. So initially, we create a Q table and we put all the values in the Q table as 0 value. Okay. Then what we do? Well, we execute one action in the environment. We go to the environment, we select one action randomly, we execute it. What is the result of that execution? We'll get the next reward. Sorry, we'll get the reward, and we also get the next state from the environment. Once we got the reward and the next state, right, then we update our Q table values. And how do we update? We update using this equation, same equation that we solved here. So with 1 minus alpha, we keep the same Q value of our current state and action pair. And with alpha, right, we add whatever reward we got and what is the maximum Q value of the next state. What is the effect of this? Well, the effect of this will be it will update some of the Q values in the Q table. Okay. And then what we do, we keep on updating our Q table with that equation. So we keep on running that equation and again executing actions into the environment, right? And we keep on updating our Q table values. What will happen after so many iterations? At the end, you'll find that the values are not updating anymore, right? The values are converged, and they're not changing a lot, right? They're remaining same. Okay. And once that happens, we stop Q learning, right? And then for whatever actions in a particular state, the Q value is maximum, we take out those actions and create our policy, and that is called optimal policy. And hence we solve our problem, right? So what I show you here is, this is a famous mountain car problem. Okay, so in the previous slide, I showed you this is a control task, which is called balancing an inverted pendulum, okay, or a cart pull problem where you have to balance this rod. Okay, this is one of the famous, you can say, benchmark problem in reinforcement learning. Many advanced algorithms are also tested on these kind of initial benchmark problems. And this is another one where, if this is called mountain car. So if this car will just try to move in the forward direction, it will never reach the top of the hill, right? So, in order to go forward, the best course of action is actually to go backwards to gain momentum and then to go forward. So these kind of interesting controls you learn using reinforcement learning. Okay. So, right. So now to end this session, whatever we discussed till now, or at least specific to this Q learning, right? It maintains this table of all Q values, right? How about, right, if you go to real world, right, and the number of possible states or states, even if this is only the state, the number of possible states that are there is so enormous that you can never actually create such a table and store it in the memory. There are simply too many states, right? How do you solve such problems then? We still want to use reinforcement learning in such problems, right? So how to deal with too many states? Okay, one answer to it is called function approximation, where we say that, you know what, I'm going to generalize these state actions with a set of parameters called W. So I'm going to fix a set of parameters for each state action pair. And now instead of storing this table of Q values, I'll just focus on learning these parameter values, which could be 5 or 10 parameters or 20 parameters or whatever. It will be much less than the number of states or state action pairs. Okay. And then I am going to create a function out of it. So whenever now you need the Q value of a state action pair, you input the Q value, right? And I'll give you the best, I'll give you the Q value of that particular state action pair. Okay. And then learning problem now reduces to learning these parameters that can always give you the best or the actual Q value of a state action pair. And this way, the complexity of storing, enormous amount of state actions, that goes away. Now we just have to learn a function using function approximation, right, for a set of parameter value W. And with this, we will be able to get the Q values. Once you are able to get the Q values or the best Q values, you can always extract the policy. Okay. Well, easily said than done, right? Because learning the parameter, and since it is an approximation, there will be approximation error and so many other issues to deal with. Okay. And that will be the task of the next session.